Today we're going to be looking at a box which is going to be sliding from rest down a ramp, and it's a rough ramp, so there's friction involved. And we're going to look at the work done by gravity and also how much mechanical energy it loses in the process due to friction. Remember, mechanical energy is only conserved in the absence of friction. And so since there is friction here, it will lose some of that mechanical energy to work done by friction. And we'll see if we can calculate that amount. This corresponds to questions 8, 9, and 10 on Work and Energy Part 2 homework. Alright, so it says that starting from rest, a 6.0 kilogram block slides 2.1 meters down a rough, that's code for friction, a rough 28-degree incline in 3 seconds. The acceleration due to gravity is 9.81 meters per second, and they'd like us to find the work done by gravity. Okay. Now remember, all work is equal to force times distance. However, it's not just any old force. First of all, you need to choose the particular force that you're asked about. And so, since we're asked to find the work done by gravity, we will need to use the force exerted by gravity and the distance it is exerted over. Once again, though, we can't just use, remember that gravity in this case actually has two components, both the x and the y. And so if we sketch this in as the force due to gravity, then we would say, hey, our components are going to be FGY and FGX. All right, and see, we'll go ahead and label all three of those things. Remember, always nice to have a good free body diagram to work with when forces are involved. So there's FGY and FGX. Now remember that we need to use the component of the force that is in the same dimension as the distance covered. In other words, we need to choose the force that is parallel to the distance that is covered. And in this case, the distance covered is along the ramp, so we need to choose the component of the force that is along the ramp, and so that'll be FGX. So to find the work done by gravity, we need to choose FGX if we're going to use distance d. We could actually use the whole component FG if we wanted to recalculate the distance covered, which would be then the height. But no need to worry about that since we can find FGX easily and we're given d. Alright, so the work done by gravity then is equal to FGX. FGX, of course, is equal to FG times sine theta. Remember that through miracles of geometry, theta in this angle of this triangle is the same as this theta angle here. And so then we would use our sine function in order to find the value for the opposite side. Alright, so FG times sine theta will give us FGX. FG is equal to the mass times the acceleration due to gravity, and then we could multiply that by sine theta to get FGX. You substitute in values of 6 kilograms and 9.81 meters per second squared. Times sine 28, and then you'll find that FGX is equal to, is equal to 27.63. So FGX equals 27.63 newtons. All right, excellent. And so we'll bring that up here and substitute it for FGX, 27.63 newtons. And then we'll multiply that by the distance covered, which is listed as 2.1. So times 2.1. I'm going to take 27.63 and multiply it by 2.1. Then I end up with 58.4 58.03, approximately 58.03 joules of work. So 58.03 joules, the work done by gravity. Remember, when you're entering that into your homework, you'll want to preserve enough decimal places that you're within 1%, that you don't round to more than a 1% difference. So just be cautious about that. All right, the next part of the question asks for the change in mechanical energy. So we're looking for the change in mechanical energy due to friction. All right, change in mechanical energy due to friction. There are actually several ways to find this. I'm just going to select one. And in this case, I'm going to calculate the work done by friction. Remember, if you have a loss of mechanical energy due to friction, that change or that loss, and we know it'll be a loss because we've started off with a certain amount here, and even though that some of that energy will be transformed into kinetic energy as it slides, some of it will have to be used to do work against friction since it is a rough surface. And so that change or loss in mechanical energy is going to be equal to the work done by friction. And remember that the work, any work, is force times distance. And again, so the work done against friction will be equal to the force of friction times distance. Now our distance is still 2.1, so in order to find that value, we just need the force of friction. Well, that's not immediately available. I'll tell you what, I never did complete my free body diagram, did I? Let's go ahead and do that now. We'll have the normal force acting up that direction. And since it is sliding downward, we'll have friction acting up the ramp. So there's the force of friction acting upwards. Now, some people will be tempted to draw FA in there. They say, hey, it's got to have some kind of force moving it down. Well, it does. Thank you very much. That's FGX, and we've already got that sketched right there. So please don't be adding FA to the diagram. There is no other force. There's no little gnomes or dogs or anything else pulling the box down the ramp. Just gravity. So no additional forces. All right. Well, let's look at this. These are not balanced because it's accelerating down the ramp. We know that because it goes from rest and increases its speed to something else over the course of 3 seconds, and it covers this much distance. So we know then that, well, gosh, who did that? All right, well, that was unexpected. Who just grabs the title bar when they mean to keep writing on the surface? I don't know. If we find out, though, we'll speak to them about that. All right, pressing on. So, as we were saying, it is going to be accelerating down the ramp, which means there will be a net force. Now, that net force is going to be equal to the difference between these two. So Fnet will equal Fgx minus Ff. Okay, and so we know Fgx, so if we can find Fnet, then we'll be able to solve for Ff, and that's really what we're trying to do here. So, gosh, if only there were a way to find Fnet. Well, I seem to remember that Fnet is equal to m times a. All right, well, I know m, so if we've got a written down somewhere, then we'll be able to find Fnet. Well, no such luck. A is not, in fact, sketched in yet over there. I'll tell you what. Let's see if we can find A. And this is where we're going to use one of our old kinematic formulas from way back at the beginning of the semester. And you'll recall that delta x equals VIT plus 1/2 AT squared. All right, so if you don't recall that, hopefully you've got a formula sheet nearby that you have that written down on. Don't suppose it matters now that I've written it for you, huh, does it? So let's see, slide this thing back out of the way again. And we see that our delta x, our distance covered, is 2.1 because it's sliding along the ramp. So 2.1 equals, now our initial velocity is 0. So that's going to zero out that whole term, plus 1/2 times, it is not in free fall, it's sliding along the ramp. And remember that A is actually what we're looking for. And T is, well, 3. So that's convenient. We'll put 3 there. We'll square it. and then we'll press on from there. So 2.1 will equal 4.5a, if I'm squaring that correctly, and then multiplying by 1/2. And so 2.1 will equal 4.5a. And when you carry out the math, you find that a then equals 0.46 repeating meters per second squared. Don't forget that unit. All right, well, let's bring that up here and substitute that in. Our mass is 6. Our acceleration from below is 0.46 and some change. And so go to the handy-dandy calculator and multiply those out. And you end up then with an Fnet of 2.8 newtons. And in fact, when I used the original calculated value and multiplied it out, I ended up with exactly 2.8. So that was awfully convenient. All right, well, 2.8 equals FGX 27.63 minus FF. Okay, and we see, so at this point we swing FF around to the other side and it becomes positive. Swing 2.8 to the other side and it becomes negative, so essentially subtracting 2.8 from each side and adding FF to each side in one step, and we get 27.63 plus 2.8. Whoops, who does that? Minus. There we go. Remember, subtracting 2.8 from each side. Sorry about that. So as we do that, we'll then find that FF is equal to 27.6 minus 2.8. And we end up with 24.8331. All right, so now at this point we have the force due to friction, and we would need to put that in here. Now here's the trick to remember at this point. Remember that since friction is acting up the ramp and the distance covered is down the ramp, those are in opposite directions, and so one of them needs to have an appropriate negative sign. Remember that all this time when I'm working with these forces, I choose to work with magnitudes and just set the appropriate signs in place based on my directions from my free body diagram. Well, at this point I need to do that again because the appropriate sign and for the force and the distance is going to be opposite. So the force of friction will be negative 24.8331 times our distance 2.1. And when you multiply all that out, you end up with 52.15. Again, that's negative because those are in opposite directions, so negative 52.15 joules. And please don't round prematurely since you'll be putting that value into a computer. All right, and again it asks for the change, and so that is a negative value because it is a loss. We are losing energy to friction, and that's the way that the universe works. All right, number 10, part 3 actually says, what is the work done by the normal force between the block and the incline? Well, again, work, remember, is always force times distance. However, it's force parallel to the distance covered. Well, the distance covered is down the ramp in our x dimension for our ramp along that x-axis, and the normal force is exactly perpendicular to that. So there is no component of a normal force in that distance, and so there is no work done by the normal force. So the work done by the normal force is equal to 0 joules because no component of the normal force is parallel to the distance covered. So the normal force does no work whatsoever. All right, thanks very much. I hope that was helpful, and thanks for watching.